It is often useful to make a quick sketch of what the wave function looks like because we can learn a lot by looking at what that wave function looks like and then being able to think about the square of that wave function, which tells us about the probability of the particle being in a particular region in space. So one of the ways in which we typically visualize these systems is by not only thinking about the wave function, but also thinking about the total energy and the potential energy. So let's think about our particle in a box system and see how we typically do this. So the first thing is that we sketch the potential energy function. And so for our particle in a box, it looks like this. And that's going to give us our potential energy. And then we draw, as we have been doing, the total energy possibilities, the possibilities for the total energy on this same axis. And so even though our potential energy is 0, we have a total energy that's associated with the quantum number 1, n equals 1, and that total energy, right, has some value. The next possible energy, that corresponds to n equals 2, is higher up at a higher energy, so we draw that up here at a higher energy. And then the next one, that's n equals 3, is even higher than that, and so we draw that here. So we have the total energy axis drawn on the same picture, the same scale as our potential energy. The next thing we do is to draw in what our wave functions for each of those energy levels look like. So here's where we sketch the wave function, and we're going to use the total energy line as our x-axis for the wave function for n equals 1. And then when we do n equals 2, we're going to use this line as our x-axis, right? So our first wave function in the particle in a box looks like this, and our second wave function looks like this, and our third wave function looks like this. And how we got those particular wave functions is what we're going to look at in this video. We're going to see how I knew to draw them in that way. The easiest way to see how to sketch a function is to figure out two things about the function. So we want to know what x's maximize or minimize the function, and we want to know the nodes of the function. So a node is a place where the function, or in our case, psi of x, crosses 0. So goes from being positive to negative, plus to minus, or minus to plus. So those are what nodes are. We know how to maximize or minimize a function. We know how to find the x's that maximize or minimize a function from calculus. So we know that if we take the derivative of the function and set it equal to 0 and then solve for x, that will give us the minimum and maximum values for our x's. So if we take our particle in a box function that we know already, and we find the derivative of that function, we will find that the derivative is square root of 2 over L n pi over L cosine, because derivative of sine is cosine, n pi x over L. And I got this extra n pi over L because I had to take the derivative of what's inside. So we're going to set this equal to 0, and that's going to give us our max and min values of x. So we can see that these constants are never going to equal 0, so the only way that this is going to equal 0 is if this cosine equals 0. And cosine is 0 when the argument, so in this case n pi over L, x max or min, is equal to an odd value of pi divided by 2. That's where cosine is always going to be 0. So for each wave function, for each value of n, there are a possible number of maxes and mins for my wave function. So let's look at psi 1 first, where n is equal to 1. So if n is equal to 1, and I want to solve for x max or min, then I'm going to put 1 in here, and I'm going to solve for x. And so I have 2c plus 1, and my factors of pi are going to divide out. 2c plus 1 divided by 2 times L. So every odd value over 2 times L is going to be a max or a min. So I can have a max or a min at 1/2 L, so L over 2. And then the next possible one is 3L over 2. But remember that 0 is less than or equal to x is less than or equal to L. And 3L over 2 is bigger than L, so it's outside the range of my possible x's. And so this is the only max or min for psi 1. I can do the same thing for psi 2, and I'm going to find that the max and mins for psi 2 are 2c plus 1 times L over 4, which is going to give me values for max and min x's of L over 4 and 3L over 4. I can't go any higher than that, because if I go higher than 3L over 4, I get outside my bounds for x. So that's how I find the maxes and mins for my different wave functions. Let's see how we can find the nodes of these wave functions. So the nodes are where we go from plus to minus, so it has to be where we cross 0, right? So our wave function itself has to be equal to 0 at a node. So I take my actual wave function, 2 over L sine n pi x over L, and set that equal to 0. So that's going to be 0 when the argument, so x of my node values of x, are going to be integer values of pi, because that's where integer values of pi is where sine is equal to 0. And so if I solve for the x for the nodes here, again, my factors of pi are going to divide out, and x is going to be equal to CL divided by n. So for my nodes of any given wave function, it's going to be some integer value of L divided by n, where n is the quantum number that describes that particular wave function. So for psi 1, for my first wave function, I can have c is equal to 0 would be 0, right? C is equal to 1 would be L. But here's the thing. 0 and L are not nodes because the wave function cannot exist past 0 or L. So even though psi equals 0 at 0 and psi equals 0 at L, it doesn't cross. It doesn't go from plus to minus or minus to plus. So these are not nodes. So the endpoints of my range, are not nodes. So there are no nodes for psi 1. So psi 1 has no nodes. Psi 2, on the other hand, has nodes where I have L over 2. So here I've made C equal to 1, N is 2 for psi 2, so L over 2. So L over 2 is a node, and then 2L over 2 just gives me L, and I know that L is not a node, so that's the only node for psi 2. So psi 2 has a node in the middle of the box. So now if we think back to the wave functions that I drew, we can see why I drew those wave functions. So we said that psi1 has no nodes, and it had a maximum at L over 2. So if we look at the function we've drawn, there's a maximum right in the middle of the box at L over 2, and there's no place where the wave function crosses the x-axis. Remember that we're using this energy level as our x-axis for this wave function. And then when we look at our psi2, we said that psi2 had a node at L over 2, and it had a max at L over 4 and a min at 3L over 4. And so we can see that we have, in fact, a crossing, a zero crossing right at L over 2, and we have a max at L over 4, and we have a minimum at 3L over 4. And if I want to convince myself that these x's that I've calculated as maxes and mins are maxes versus minimums, I plug that number back into my wave function and see whether it's positive or negative. The minimums will always be negative and the positives will always be positive. The maxes will always be positive. And so that's really how I can visualize or sketch a wave function, is to find the nodes and the maxes and mins, and that helps me to actually just draw what that wave function looks like.